So I think one of the reasons why it's so surreal to be up here giving this talk in front of you today is because it feels in some ways like it was just yesterday that I first came to my first ever AGU meeting, which was when I was a master's student with Doug Burbank. About 15 years ago, actually. And I remember he said, okay, to me and my grad mates, I think you should all get in the car and drive up the road and go to the AGU meeting and then to this funny little meeting afterwards called the Gilbert Club that I didn't quite understand or know I was a part of. And ever since, both of these meetings have been the highlight of my professional year. I guess now is about as good of time as any to admit publicly that when I showed up at Santa Barbara, I had never even had so much as a class in geomorphology. So my surface processes understanding was quite limited. Sorry, Doug. I think I had read a couple of his papers about his work in the Shawalics in the Himalaya. And I had it in my head that I was going to go and be his master's student and I was going to solve some big structural problems on fold thrust belts in the Himalaya or something like that. Those were my ideas, not his. And when I showed up, he said, hey, how about you work with my new postdoc, Eric Kirby, and you guys can study the rivers that drain these little mountains here in the backyard. And I remember thinking, oh, okay, yeah, that sounds as good as going to the Himalaya. Yeah, that's probably okay. But actually, this was one of the best things to ever happen to me in my life. What I learned working with Doug and Eric was to be exceptionally fascinated by the landscape, and they helped me to understand how surface processes and tectonics link together. And it was just an amazing time for me. I learned so much. And because I was such a blank canvas, it was an amazing time for me. It was like a sponge. Everything I was learning was so new and fascinating. And if you're going to stumble into geomorphology, this was a pretty amazing place to do that because not only was I learning from Doug and Eric, but I was learning from the likes of Tom Dunn and Ed Keller and Doug's other postdocs, Manny Gabay and Mike Oskin and Nathan Nimi. So this was just an amazing group of people to be learning about surface processes from. And at this time, Tom was doing something really awesome, which was he would invite us to his home in the evenings for a seminar where we would discuss papers in surface processes and have delicious desserts. And it was at Tom's house that I first learned about Libby Leopold and his scientific legacy. And it was also during this time that I started to learn more about our geoscience forefathers and some of the revolution ideas that they had very early on. And it didn't take long for me to start to have this realization that, geez, these guys figured out a lot of stuff a really long time ago. And you can't help but say to yourself, like, what's left? I'm sure other people in the audience have had this realization many times where you've come up with something that you thought was absolutely brilliant, only to find out that Gilbert actually did that in the late 1800s. And so... it's fun to think about some of these early ideas and how amazingly clever they were early on. And it would be easy to think that we've done it all. It's already been done. But of course, that's not true. And in fact, in the fields of surface processes, I'd say that we're in a really amazing place right now because there's been some really revolutionary advances over the last few decades and even really over the last few years that have allowed us to do all kinds of things that we could never have dreamed before. We have a much better understanding of geomorphic transport laws. We have really improved computing, which is allowing us to do things like numerical modeling, using GIS and other forms of modeling. We've got really exciting new and improved thermochronology and geochronology resolution, including detrital data sets that are allowing us to get rates of erosion and in some cases uplift over really large scales spatially and temporally. And of course there's LiDAR and high resolution imagery and drones and the global infrastructure. Things like Google Earth are really changing the game for us. And so we can make a lot of new discoveries with these techniques, but we can also revisit some really old questions, some long-standing ideas and problems, and start to really tackle them and test them in ways we couldn't before. And so this is a really exciting time for our community. So I've been fortunate enough to be able to take advantage of some of these new advances, and I'm going to highlight three case studies for you today for the rest of this presentation. I'm going to talk about landscapes at the scale of an orogen, and in particular, I'm going to talk about the detrital erosion data set that Marin alluded to. And then I'm going to talk about landscapes at the mountain fault scale. And in particular, I'm going to talk to you about work that I've been doing related to the geomorphology of strike-slip fault zones. So I'll show you a suite of some numerical experiments and then also a couple of field locations. And then finally, I'm going to briefly wrap up with some new work at the scale of a hill slope, which is related to some LiDAR data and carbon-14 dating that we've been doing on some western Washington landslides. And then I'll just close up with some final remarks. So, as Marin mentioned, the project that we worked on in Tibet had just a whole host of collaborators, and so there's a lot of people to acknowledge. I can't name every single person, but I certainly want to acknowledge her. It's a special privilege to be somebody's first PhD student, and I can't thank Marin enough for trusting me with that honor. She brought me to Asia, after all, to work on the big problems that I was interested in. And she pushed me to think deeper than I ever had before. And I mean that both figuratively and literally, as she helped me to start making connections between the surface and the deeper crust. It's also hard for me to put into words how important and impactful it was to have a strong female scientist as a mentor in a male-dominated field. I can only hope to be as inspirational to other young women as Marin has been to me. So thank you, Marin, for showing me the way. I also want to acknowledge Peter Molnar and Zhang Peizhen, whose vision and funding prowess made this work possible, and of course to the NSF and the Chinese NSF for funding it. And finally, I want to acknowledge my dear friend and grad mate, Boris Avdiv, who played a significant role in this work. He is no longer with us on Earth, but he inspires me daily, and I'm sorry that he's not here today. Okay, so few places on Earth have inspired Earth scientists or fascinated us more than the Tibetan Plateau and the Himalayan orogenic system. And that's for good reason. You can see from this photo that this is a really impressive geologic feature, arguably the most impressive geologic feature on Earth. We've got crust that sits at elevations of around 5,000 meters. It extends almost half the size of the United States. And of course, the southern boundary of this plateau is the Himalaya, the highest mountain range on Earth. We, for the most part, as a community, can agree that the plateau and the Himalaya are in some way related to the collision of India and Asia that started as continent collision about 50 million years ago. But that's almost in some ways the last thing we all agree on. We've had a lot of debate about exactly how this plateau got so high and so thick and when it happened. And this is despite the fact that if you open pretty much any geologic textbook, you're going to see the Himalaya and the Tibetan Plateau as the type locality of continent-continent collision. And yet we still have so many questions about when we would even expect to see something like this and how it forms. This has also been sort of ground zero for tectonics, climate, erosion, interplay questions. You know, every year at AGU, there are sessions devoted to this really intriguing topic. And so this place has served as one of the natural laboratories to study it. Because if you're going to build mountains in a plateau as big, as bad as Tibet and Himalaya, you can actually start to ask questions about how the lithosphere and the atmosphere might be interacting, either regionally or even globally. So most of, well, maybe not most, but many of our steps forward in terms of understanding the evolution of the Tibetan Plateau have actually come from the erosion record. I think it's important to note, though, that if we look at the plateau, which I'm showing here on this globe, which does give you some sense of the scale of this feature, if we take the plateau, we can actually divide it into two sort of gross geomorphic terrains, which are shown here in this figure from Clark et al. 2006. So you can see this green area here, this is the part of the plateau that's internally drained. So this is where all the lakes are that you've probably seen. And then this part of the plateau is a beautiful flat erosion surface with rivers that are drilling down into it. And there's some really impressive gorges down here as you get to the southeast flank of the plateau. And so we have information about erosion in both of those locations. So some of the earliest work was actually done in the internally drained part of the plateau. And as you might imagine, up in this very high arid region where it's internally drained, the erosion rates tend to be rather slow, and the thermochronology cooling ages tend to be older. If we look at the other part, and many people have studied, especially down on the plateau flanks and edges, what you see is much faster erosion and younger cooling ages. And if you focus in on some of those gorges, it looks like they were formed sometime in the mid to late Miocene, and people have used this as a proxy for the uplift or rise of the plateau. I want to point out, too, that it's really important that these are in the externally drained part of the plateau, these rivers are going out to base level. So this is really important, right? Because if we're going to try and make some connections between uplift and erosion, then we need to make sure that we're pointing to global base level here so that we can actually make those connections. But so for our part, we wanted to think about the area on the plateau that was up in the highland, but outside of the internally drained part of Tibet. So we wanted to ask the question: in this area here, up in the headwaters, does it look more like the internally drained, sort of slower part, or does it look more like the downstream part where something has been happening and erosion is more rapid? And we're also interested in looking across the entire width of the plateau to see if we might see any differences as we move from south to north, anything that we might be able to connect with the timing of when this plateau was built. And so in order to do that, we decided to go with a detrital sampling scheme, and we were using low temperature thermochronology. And we wanted to use detrital sampling because, as you can imagine, this stretch extends over 750 kilometers. And this is in a very, very remote part of the world. So it's not easy to collect a lot of samples through here. So we let the rivers do the work for us. So here's a little schematic showing you that we can scoop up a grain, not a grain, but a bag of sand at the mouth or outlet of some river. And then we analyze the detrital grains, and we hope that they've come from all parts of the basin here. I should note that this work was done in the Noble Gas Laboratory at Caltech in collaboration with Ken Farley. And as I mentioned, we used low temperature thermochronology for this work, so apatite, uranium, thorium, helium, and fission track. These have the lower closure temperatures, which are telling us something about the erosion of the upper 2 to 4 kilometers of crust. Okay, so here's our sampling strategy. We picked up bags of sand at each of the places where you see these yellow dots, and we sampled the modern river sand from 8 catchments that are tributaries to the major rivers that drain the plateau. We did our best to avoid Cenozoic volcanics or sediments or faults because we were really interested in sort of the gross geomorphology here. We wanted to figure out patterns across the plateau, and we weren't so interested in the local effects from any single fault or volcanic cooling. All right, so before I start showing you the results of this, let's do a simple thought experiment about what we might expect to see. So we might expect to see a spatial progression in ages from the south to the north. And what I mean by that is that most of the models, or many of the models for how the plateau has been built, whether it be through a continuum or from a stepwise growth sort of plate model, they both predict that you would have the plateau building from south to north through time as collision proceeds. And so if that's the case, we might expect to see our youngest thermochron ages in the north and our oldest thermochron ages in the south. Alternatively, we might expect to see uniformly old ages across this whole area. And I say that because, and I've switched now to an image that sort of gives you a sense of how arid and dry the upper parts of the plateau are. So it's possible that, the erosion up here would just be slow, and we wouldn't learn much from it in terms of any sort of spatial progression. And that's also in comparison to as I mentioned before, the margins of the plateau where it's wetter, the rivers are carved more deeply in. And then finally, there are also models for how the plateau were built that involve a more uniform style of uplift, right? And so things like lower crustal flow or a root loss that generated a buoyant rise in sort of a sudden fashion. If this were the case, we might expect to see uniform ages across our catchments, but they wouldn't necessarily be old. They would be perhaps younger, heralding the timing of when that uplift occurred. Okay, so here's what we found. It's hard to digest this, so I'm gonna hit the high points in a second. And sorry for using the mouse. They've asked me to do this because it's being filmed and you can't see the laser pointer, but it's hard for me to see the mouse, so I'll do my best here. So I have the helium ages on the left and the fission track on the right. And what these are basically simple histograms of the ages. So this is from 0 to 280 million years. And this is a histogram, so you're just looking for bins that show the different ages that we found in the catchments. And then the inside here shows the hypsometry, or the range in elevations in each of these catchments. And I have them oriented from north to south across the plateau. And so I realize that it's hard to see that, so I'm just going to summarize what I think are the key points from these age distributions. The first thing is that what you can see is that there are very similar age ranges in all of these catchments. And importantly, because there's a connection in thermochronology between age and elevation, it's important to note also that these catchments all have very similar elevations as well. And so if you have a similar range in ages and similar hypsometry, that suggests, just from the raw data, that the erosion histories are similar from across all of these catchments. The other thing I want to point out is that there is a very large spread in ages here. You can see that, and these are just the yellow and the yalong. I'm zoomed in on those, but they all look very similar, where you have ages that range all the way from less than 5 million years to up into the Mesozoic, all preserved in these catchments. And that tells us, even before we do any modeling, that the erosion rate must have increased at some point in order to explain this age distribution. So in order to get those really young ages, we have to have relatively fast rates of erosion. But that rate change in erosion couldn't have happened, had to have happened sometime long enough ago that you actually still preserve the old ages in the catchments as well. So this is really quite telling, and it tells us that this erosion record has information in it that can tell us something about when a distinct change happened. So that's very exciting. But in order to get that information out, we need to do some type of modeling. And in the past, it's been really difficult to do that with detrital data sets in thermochronology, or really in any detrital data set, because you often have to just assume that the erosion rates haven't changed through time, and then you go for some sort of an average. But in this case, we applied an inverse model that utilized Bayesian statistics and a Markov chain Monte Carlo algorithm in order to actually figure out when those changes in erosion might have happened and what the rates would have been. And so the inputs are actually fairly simple. The inputs are the detrital ages and the basin hypsometry, and then a range of some reasonable prior probabilities. And then the model estimates probability distributions of erosion rate and depth to closure isotherms to determine probability distribution of bedrock ages. So what we essentially get from these model output are what the age elevation would be if we had basically a bedrock transect in that same catchment. So we can look for changes in erosion rates through time, or so-called breaks in slope. Okay, so we considered a whole range of models. For the sake of time today, I'm not going to be able to show you all of them. Instead, I'll just show you our most flexible model, the one that seemed to fit the data the best. And that's a model where we considered all of the catchments to have a similar erosion history. So we modeled all the data together. And then we allowed for up to 2 discrete changes in erosion rate through time. And here's what we found. So this is a plot of elevation versus age. So these might be, for those of you familiar with age elevation plots in low temperature thermochronology, these are sort of the plots where you're looking for a break in slope. The green line represents the fission track, and the blue is the helium. And then again, I have the catchments from north to south. And then over here, what I'm showing is I'm going to summarize the timing of the erosion rate increase, and this is distance from north to south across the plateau. And so what you can see just from looking at these before I even go into the plot on the right is that clearly there was a big change in erosion that happened relatively recently. But before that big change happened, there's actually a very subtle but significant increase that seems to have happened sometime around 55 to 45 million years ago. And this, not coincidentally, is the same time when we think that India and Asia began to collide. So we see an erosion rate increase at that time, but it's actually a pretty subtle change in erosion rate. So you can see that here. The rates are still very low, still like, around something like 0.02 millimeters per year. Then the really big change happens in all of the catchments around 11 to 4 MA. And this is when the erosion rates jump up to 0.2 to 0.6 millimeters per year. And you can see that dramatic increase over here. And so this is very exciting because this kind of information is usually pretty difficult to come by, especially in a detrital setting. And so it's very exciting to be able to pull that information out using this kind of inverse model. And so we can actually take the result of this and compare with what is found on the very same rivers downstream using bedrock studies. Those are the studies that I mentioned in the beginning. And what you see is that they're very similar, actually. So these triangles represent places where age elevation relationships were found using the same chronometers. And what these workers found was that there was a big increase in erosion sometime between 5 and 15 million years ago. And the erosion rates that they found are very similar to those that we have all the way up on the plateau. And many have interpreted this this increase in erosion to be related to regional uplift and plateau expansion, possibly by lower crustal flow at that time. And so if you look at our data set this far upstream, you start to see that whatever event was happening was even more widespread than initially thought because it's overlapping in time with our data set all the way up here on the plateau. Oh, and I also want to point out, I'm just showing here that there have been more recent studies that show that there are other more localized events. So there's some evidence in this area here that there was more than one phase of crustal growth to the east. And I'm not showing it, but there are other studies too that have shown some earlier phases of deformation as well. So I want to make sure to note that. But this later phase that we're seeing is a very widespread phase. And so if we go back to where we started and ask about that spatial progression, what we ended up finding was this uniform, but not necessarily old, suite of ages. And so this suggests that we have uniform erosion histories across much of the eastern Tibetan Plateau, which points to some sort of regional uplift event at that time. And these are possibilities here for something that could accomplish that. Okay, so I don't have time to get into the strike-slip faults that cross the Tibetan Plateau today. But for those of you who are familiar with the area, you know that the strike-slip faults are one of the most prominent features across Tibet. And I only show them here to point out that one of the big inspirations for me towards the end of my PhD in studying strike-slip faults was these faults in Tibet that I was trying to better understand. At the time, I was really interested in their long-term history, but it got me thinking a lot about landscapes in strike-slip settings. And I started to realize that as a tectonic geomorphic community, we have really focused hard on uplift and dip-slip faults. But we have paid much less attention to the geomorphic evolution of lateral faults and lateral advection. And so that inspired the work that I'm going to talk about in this next case study, which is the landscapes at the scale of a mountain fault system. And of course, once again, I'd like to acknowledge our funding sources and colleagues. And I just want to make one shout out to one individual in particular, and that is Greg Tucker. Greg was very generous to me. When I contacted him about a postdoc, I told him I have this really big idea. I want to work on the geomorphology of strike-slip fault systems, and I want to work on modeling them in landscape evolution models. But I don't have any modeling experience. And now that I'm a professor and I know what it's like, it's kind of magic when a person says, "I want to be your postdoc," and I know how to do all these things. And it's not nearly as magical when they say, "I want to be your postdoc. Can you teach me more stuff?" So I really appreciate that Greg was willing to do that, and I will forever be indebted to him for his patience and kindness and his amazing landscape evolution prowess. So, when I start talking about strike-slip fault systems, I usually like to start with an image like this. And this is, of course, LiDAR from probably the most iconic strike-slip fault on the planet, and that is the San Andreas Fault. And images like this show beautifully what it is that we know about these strike-slip fault systems, which is that there's a whole suite of geomorphic forms that we're very familiar with at the fault proper. Things like offset river channels and sag ponds and shutter ridges. And paleoseismologists and neotectonicists have relied on these to help us to understand, one, where is the fault? Two, what's the sense of slip on the fault? And three, in the best cases, can we use this information to actually calculate slip rates? I have a little asterisk here that sometimes we can use them to calculate slip rates. And that's because many of these features are in some ways ephemeral, right? So if you're looking at the offset of a river channel, that might tell you something for a little while, but eventually one of these beheaded channels that's getting rafted along the fault is going to sneak up and steal the headwaters of this river. And if you were out in the field at that time and came upon it, you might actually think that a right lateral fault is a left lateral fault because it's stolen it and brought it back the other way. So these are really valuable indicators, but there's still more, I think, that we can do. And I'm going to make the case to you today that we can explore this problem deeper, that we've really only just scratched the tip of the iceberg by paying attention to just some of these features at the fault proper. But we haven't yet asked, what's the dependence on slip rate, material properties, or geomorphic process, and when these features form at a fault and why. We haven't really looked much upstream of the fault. So how do these features that form along the fault, what do they do to the upstream catchments? And then what's the landscape evolution of these strike-slip fault systems over time, over the long term? And so that is the question. These are the questions that I set out to address with Greg and colleagues using first a suite of numerical models. I think a really important starting place to probe this problem deeper is to look at a cycle that we might predict along a strike-slip fault. So we can make this prediction that we expect that the rivers that flow across a strike-slip fault are going to be in a permanent state of transience. And I say that because these rivers are going to be constantly cycling back and forth between a lengthening phase as they get stretched and elongated along the fault to a very rapid shortening phase after each river capture occurs. And this is going to keep going as long as the fault is active, right? So that means that we can predict that strike-slip rivers will be in permanent transience. This could be very valuable because if that's true, we might expect this to be recorded in the channels upstream of the fault in the form of nick points or other disequilibrium sections of river. And so if this is expressed in the longitudinal profile, might this be a useful tool in detecting slip activity? And in fact, we can think of this as a competition between the rate at which the river is going to be responding to these perturbations in base level versus how fast we're actually advecting along the fault. So this is a competition between slip rate and the erosional efficiency. So in the best case scenario, if we have rates for one of these things, we might even be able to back out the rates of the other. But if nothing else, we might have a really nice relative indicator if we, say, compare rivers along two different strike-slip faults. All right, so as I mentioned, we decided to try and see if these predictions hold true, and we did this first with a numerical model. And that's because, it can be really challenging to find the right landscape in the field where you would actually have all the information that you need to be able to track these kinds of changes through time. And so that's something really valuable that numerical modeling provides. And so we did this with the child landscape evolution model, and I show here just the simple governing equation for land surface elevation that's under the hood here. So we have a simple representation of both linear and nonlinear creep transport laws for the hill slopes, and then we use in these models that I'm going to show you, we use just simple unit stream power for channel incision. We also have an uplift function, and importantly, of course, we can move the grids laterally in a strike-slip fashion. So here's the ingredients for the models. So we started by building topography, and we did this until we reached some form of steady state. And then we broke a strike-slip fault across the landscape, which I'm showing here. And then we laterally shifted the grid points along that strike-slip fault, and we did this at a variety of slip rates, from as slow as 0.5 millimeters per year all the way to as fast as 20 millimeters per year in order to compare the differences that we might find. And so I'm just going to start by showing you some model output here from the really fast slip case. So this is 20 millimeters per year of right lateral strike slip faulting. Whoa, that's not right. Let's see. Okay. And so if you keep your eye on some of those rivers, what you see is all of the captures and the lengthening that we were so excited to simulate. And there they are. So you can see that if you keep your eye, sorry, I should say that the red, I can play that again, is this is colored by topography. So red are high slopes, or high elevations, blue is low elevations, and I'll play that again. And there we go. And what you can see are those, the rivers are really quite dynamic, as we would predict. And you can also see that the spacing is really setting the time scale of those captures, right? So you never really have an offset that's much longer than any of the longest spacing between any of those original catchments. Okay. So it would be most effective, I think, for us to take some snapshots in time as the model runs and look at the longitudinal river profile of one catchment through time so that we can see what it does. So I'm switching now to showing you first a slow slip rate case, and then I'm going to show you what the fast slip rate case looks like. So we're going to start with 1 millimeters per year, and this is the river catchment that we're going to be focusing on. And here is the longitudinal profile of that catchment. This is right after the model starts, so we've only had just 500 years of slip here. So actually this is 1 millimeter per year, so we've had just hardly any offset at all. You could see a fine little profile to start with. Here's what it looks like after 120 meters of offset. So what we've done is we've lengthened the channel a little bit along the fault, as you can see here. And here's the important thing. This is what it looks like after capture. So this is after 150 meters of offset, we have a river capture happening here. And what you can see is there is a very large discontinuity in the channel. So we have a really big nick point there that shows that disequilibrium that there's a disequilibrium in the river post-capture. Okay, so now let's compare that to 10 millimeter per year slip rate case. So we start with the exact same river profile, and we're looking at the same catchment. Oops. And what you can see here is that after the same amount of 120 meters of offset, it looks very different than the slow slip rate case, but this is the exact same amount of offset. So you can see here that the channel has, the channel has lengthened along a shutter ridge there, and you see a really big convexity in the channel. So this was unexpected. So what we're seeing is that basically in the fast slip case, and this is the slow slip case for comparison. In the fast slip case, what's happening is you're compounding the convexity as you lengthen the channel. So there's basically, in this really fast slip case, there's not enough time for the channel to respond to that lengthening, right? So it's getting lengthened along a really flat part, right? So every piece of channel that you're adding is over a really flat elevation there. And so you basically end up with this convexity along the fault-formed part of the channel. And that's only true in the fast slip case. Okay, so here's what it looks like after capture. So once again, we see a nice nick point that forms, but I'll note that the nick point itself is slightly different than in the other case, and that's because we're basically suturing together two channels, right? So that's what's happening here. This is the bottom of the channel that captured it with the top of the original channel. And because the original channel developed this kinds of convexity, which was different than in the slow slip case, when you suture those two channels together, you get a slightly different form. Okay, so there's a comparison to the other nick point that you see in the slow slip case. Okay, so here is a plot that just shows the slow slip case that I showed you, the fast slip case, and then an intermediate 5 millimeter per year slip rate case in between. And now I'm actually showing you this through time. So this is 500 years before capture, 500 years post-capture, and then 2000 and 5000. And the key observation here is that all rivers exhibit disequilibrium, but even the profile form itself varies depending on slip rate. So this is really exciting because it gives us a hope of maybe using some of this in order to back out information about slip rate directly from the channel profile upstream of a fault. Okay, so far I've really focused on the trunk channels. But what about the hill slopes and what about the upstream catchments? So to look at that, I want to go back and show you another model simulation result. And this time I'm going to show you the slow slip case. And this time I want you to look at not just the ridges or the rivers, but also the ridges. And you're going to see something pretty wild, which is the ridges are highly mobile. They are moving along with the fault. They are very mobile. In fact, they're marching in some cases where a ridge is staying connected across the fault, so that even though the fault is moving, I'll play that again. Even though the fault is moving in a right lateral sense, some of the ridges are able to keep pace with the other side of the fault. And this was really shocking when we first saw it, because this is not something that you expect to see. And it was really exciting too, because it's like, wow, these hill slopes are super mobile. I was sort of just focusing on the rivers, but boy, the hill slopes are telling us something really important too. And so we thought about this a little bit more about, how is it that these hill slopes are migrating, and what really drives this? And after watching the model a lot and running a bunch of different experiments to make sure that it wasn't some sort of artifact of a grid size or resolution, we figured that actually this ridge migration is actually driven by the catchment response to the river lengthening along the strike slip fault. So basically, when you start to grow the channel along the fault, new tributaries begin to grow headwardly off of that, and you end up having channels, new channels ridges dividing, growing as they make their way towards the main divide. And when they do that, they basically swallow up neighboring catchments that are at a different point in their evolution. The thing is that none of that can happen if the fault is moving too quickly. So in this case, it's another competition. In this case, it's the competition of how fast the hill slopes can respond versus how fast you're advecting along the fault. Because every time you have a river capture, you basically start the system over again when you shorten that channel. So there needs to be enough time for both the river channels to start growing off of the main channel, and then for the hill slope ridges to respond to that differential erosion on either side. So this is exciting too, because it means that there might be some slip rate information contained in the upstream catchment and in the hill slopes. So to show that, I just have a little still schematic here that I'm showing with the slowest slip rate case here and the highest slip rate case here. And this is just 3 different time steps. And I've distilled this down to a simple line art drawing where I'm just showing the ridges in this dark gray, a ridge bifurcation point with a red dot, the spacing of the catchments in blue, and then the river channels are in gray. And what you can see is that in the fast slip case, it does not matter how much time goes by, the ridge bifurcation stays the same, the catchments stay the same size. Basically, the rivers are doing their thing. You've got catchments that are, or you've got rivers that are being captured, but nothing's happening upstream. And in the slow slip case, what you can see is that the ridges are quite mobile, the spacing is changing through time, and the point of ridge bifurcation is also changing as you're growing these new catchments and swallowing up the others. So it's a very different looking landscape depending on slip rate. And so, of course, I mean, we wish that we could just go out in landscapes and watch them change through time, but that's not possible. So what we needed was to find something at any given time step in the model that we could use to see these differences in the landscape. And so this is this is the end of a model run, and they've both of these cases have been offset the exact same amount. So this is the fast slip case and the slow slip case. And I've got these the topography just colored by aspect, just to highlight some of these differences at any given time that one might find. And what you can see is that in the fast slip case, you end up developing a really beautiful set of faceted spurs at the fault proper, because you basically are, you've got this lengthening of the channel along the fault, and you're not mobile with those divides, right? So you end up with these really nice faceted spurs, even though there's no dip slip motion on this fault at all. And then in the slow slip case, what you can see are that the subcatchments have various spacing. The catchments themselves are actually wider than in comparison to here. And the ridges are extending across the fault. So that's really different and could be indicative. And so we looked for a metric that would capture this, something that we could go measure in the field. And what we came up with was that the topographic profiles, both near the fault and away from the fault, would be very different in these two cases. Okay, so here's the slow slip case. This is a near fault profile. here showing mean elevation, and this is the away fault profile. And then in the case of the fast slip case, because you're going over these facets at the front, and because the ridges don't extend across the fault, you get a much more subdued topography near to the fault, and then the same away fault topography. So if we actually divide the mean relief near the fault with the mean relief away from the fault in this thing we're calling the profile relief ratio, you end up with a PRR of around 1 when you have these really mobile hill slopes, and a much lower PRR of around half in some cases, in the case where everything is really static and not changing. So this is exciting because this is something that we could compare to slip rate and see does it hold water. And so here's a plot of the PRR versus slip rate, and you can see very nicely that when the slip rates are low and we've got all of that ridge mobility, you've got that PRR of 1. And then in the fastest slip case, it goes down to 0.5. And this is exciting to see also that it's actually gradational. It's not yes or no, ridges are migrating or ridges aren't migrating, but in fact that it's a gradation from these really, really mobile ridges to less and less mobile ridges as you get farther and farther away. So this is exciting because it's a landscape signature. But I mentioned that these things are a competition between the erodibility, the erosivity, and the rate of how fast you're pushing the fault. So to actually try and figure out what this model was really sensitive to, we just did a dimensionless analysis of that governing equation to come up with this dimensional number here, which we're calling the advection erosion number, to see sort of how it shakes out and which variables here are important. And what you can see that what this predicts is that there is a competition between the horizontal slip rate versus the rate coefficient for transport in the hill slopes, so the diffusivity, and then the rate coefficient for stream incision or the erodibility. And so to test out whether or not these variables are interacting in this way, we ran a whole suite of new models where we were able to vary just one of these things. And here's a plot of the profile relief ratio versus the advection erosion number. And what you can see is that a beautiful relationship really falls out here, where you can see that you get that maximum ridge migration and bifurcation for these lower advection erosion numbers, things that are around 1 or near 1 or lower. And then when you get higher and higher advection erosion numbers, so if you have a really fast slip rate, but also if you have, really fast response times in the channels or the hill slopes, you end up diminishing, or sorry, I said that backwards. If you have really slow response times in the hill slopes there, sorry, the mouse likes to change the slide on me. I should stop using it for that. Then what you can see is that you have a trade-off here between how fast the landscape responds and how hard you're pushing it with the fault. So I'm just going to point out a few places where we've tried to actually go from our modeling results to field sites to see how this works in real landscapes. And I'll just start by showing this example from California. So on the top panel there, I'm showing 2 sections along the San Andreas in the Elkhorn Hills, where the slip rate is greater than 30 millimeters per year. So this is a really good example of a fast slipping fault. And then for comparison, we analyzed the Santa Cruz Island fault, which is just in the Channel Islands off the coast of Santa Barbara. This fault slips much, much lower at less than 1 millimeter per year. And when we do this calculation with that profile relief ratio, what you can see is that you get a PRR of close to half in the fast slip case and 1 in the slow slip case, which was a pretty exciting result. Okay, so now I just want to spend just a few more minutes on this case study, showing you some results from the Marlborough Fault System in New Zealand. And I just want to point out that this is work that's being spearheaded by my graduate student, Sarah Harbert, who actually has a poster right now, though she may be in this room. And so hopefully some of you saw her poster or will have a chance to talk to her later. There's no way I can cover all of the really cool results that she's found, but I just wanted to highlight 1 or 2 here. And so she's investigating the signatures of strike slip faulting in the Marlborough Fault System of New Zealand, and that's the figure that I'm showing you here. And this place is just about one of the most perfect places to test these new ideas and conceptual models that we have, because this area has 4 parallel major strike slip faults. They're all right lateral faults, and they are slipping at different rates. So the Wairau Fault in the north has a slip rate that's around 3 to 5 millimeters per year, and that is in contrast to the Hope Fault, the most southern fault, which slips at 20 millimeters per year or more. And so you've got this great gradation in slip rates. And also that the faults themselves are thought to young to the south, so that the Hope Fault is the least mature. It's only about 1 million or so years old, whereas the Wairau Fault is much older than that. And then the Clarence and the Awatiri are somewhere in between. So this is really exciting. The other thing is that the lithology is quite similar. So this is all Torles Greywacke across this main field site. So it's a really exciting place to sort of try and pull out these signatures in a real landscape. It's also a beautiful place to work. The geomorphology is just spectacular. I don't have time to get into it today, but if you're interested in how relief formed along these major strike slip faults, I'm going to be talking about that in a session tomorrow. So if you're interested, you should come by for that. But for now, I'm just going to focus in on 2 rivers, one site along the Hope Fault and one site along the Awatiri Fault. And again, remember the Hope Fault is slipping at 20-some millimeters per year, and the Awatiri is something more like 5 millimeters per year. So here's a zoom in along the Hope Fault and the Kofi River system. And this is, for those of you familiar with the area, this is Mount Fife, the Pacific Ocean behind it. And this is a really cool spot because this is a place where others have already documented a series of captures. And they've done this because there's a beautiful suite of terraces that are of known age along here, and so you can actually piece together that recent captures have occurred here. And so what is thought to have happened is that the Kofi River, which is coming off of from behind the Seaward Kaikoura Range here and sort of coming around Mount Fife, the idea is that now it comes out here, but that it used to come out this way, and that this capture happened somewhat recently and grabbed the headwaters here, and now they're going this way. You can follow. There's a guy over here that's probably going to start stealing some headwaters over there not too long from now. And there's been a series of other smaller captures kind of in dominoes like we saw in the model that happen as you go through this area. And so what you can see is that Sarah has color-coded in pink places where there are nick points, and there are many nick points in these channels, which suggests that this is an area of high disequilibrium, which we would predict for a fast-slipping fault that has recent captures. And then I'll just show you what the Kofi River looks like, and you can see there's a nice nick point preserved in that channel. If we go up to the Awatiri Fault, we actually get to get a snapshot in time of pre-capture. So here is a really nice image that shows a beautiful shutter ridge along the Awatiri Fault. There's the Awatiri Fault. This is the mountains behind it. And then there's this really nice shutter ridge. And there's channels that are being moved around it. And here, what you can see is that, and again, this is also the slower area. So not only is it doesn't look like it's about to happen for capture rather than just have happened, but also that captures probably happen less often here because the slip rate is slower. And what you can see is that there's an absence of those pink dots that Sarah mapped out in the other area. So we don't see nick points above the fault along this stream reach. And if we look at the Lee Brook, which is the little stream that's getting routed around that shutter ridge, what you can see is that there is a convex piece of that channel as it kind of comes around and goes into that shutter ridge there, which is what we would predict to happen from the model in a somewhat fast slip case. Even though it's slower than the Hope Fault, it's still slipping at 5 millimeters per year. And what you can see is that the river has developed a slight convexity there. And out in the field, when we go out there, you can see that it's really backed up in a grading behind that shutter ridge. And someday soon, it'll likely find that its headwaters are stolen by the neighboring catchment here, which is primed and ready to grab it across the Epcot saddle. I think we're excited about this. We're seeing some things in the landscape that look a lot like what we found in the model, but I don't want to be, I don't want to imply that everything is working exactly as we predict, because Sarah has also found a lot of peculiarities or things that are different than the model. So one thing is that she's found that there's far fewer lengthened channels than we would predict in this landscape. And so she's been working to think about, now she's working to put sediment in these models, to think about things like avulsions and a grading, things that would likely matter in these settings that we have not considered yet. And she's also putting uplift across the fault, and she's thinking about how essential these shutter ridges might be by changing around their geometries as well. So I encourage you to go find Sarah and hear about her great results. if you've been sitting there for the last few minutes trying to figure out how it is that the word Kaikoura seems so familiar, even though you don't work in New Zealand, it might be because there was a really significant earthquake there not that long ago. So a magnitude 7.8 event that ruptured, at this point, over 10 faults and counting. This is an amazing landscape response to a single event. And so we're really excited to get back out in the field there in January and actually go see with our own eyes what the landscape looks like after a single rupture. And for those of you who are interested in hill slopes and landslides, you've probably been dazzled by all of the amazing pictures online of the thousands of landslides that were triggered, and really big landslide dams too, from this event. Which brings me to my last small case study. This one's more brief, I promise. So now we're going to talk about landscapes at the scale of a hill slope. And I was really thrilled, honestly, and so happy when I got my job a few years back now at the University of Washington. First and foremost, because I was getting to join a department with such a long-standing tradition of excellence in surface processes and colleagues that I was just dying to work with on these problems. But also because I was really excited to get involved with the Quaternary Research Center, the QRC. And it's through my involvement with the QRC that I was able to interact with a different Leopold. And that, of course, is Estella Leopold, Luna's sister, who is a brilliant biologist and paleobotanist and has an amazing scientific legacy of her own. So I'm very fortunate to have interacted with her in that way. And it also brought me to the land of the landslide, and it brought landslides to the forefront of my mind and got me working on really exciting projects much closer to home. And got me to work with colleagues like Dave Montgomery and other fellow Pacific Northwesterners like Adam Booth just down the road at Portland State University. And it allowed me to recruit awesome grad students like Sean LaHusen here to help work on some of the landscapes right near to the University of Washington. So what I'm going to do for the next few minutes is just talk about some of the work that we've been doing to date landslides in the North Fork Stillaguamish Valley. And many of you are probably familiar with the Oso landslide. And that's because this wasn't a landslide that just affected our region. This affected the whole country, really. This was a huge disaster. We lost 43 people during this event that happened in March of 2014. That's the largest landslide disaster in the United States history outside of Puerto Rico. So it was a huge tragedy. I'm showing a picture of it here. And you can see with the LiDAR next to it that this was an amazing event, a very long run-out event. And most of the people who lost their lives were living in the Steelhead Haven community, which was just on the south bank of the Stillaguamish River here. And a few really unfortunate people who happened to just be driving down the road on a sunny Saturday when the glacial hill slopes gave way in a really spectacular fashion, totally unexpected. So you can imagine that after this event happened, there was a lot of questions about why this happened, what was the cause and the trigger, and also how common are these kinds of events in this valley and in other valleys like it, all along the western front of the Cascades. And so to answer that question, you can have a look around in the landscape. So the first thing one could do is to look at the LiDAR imagery and also the previous geologic mapping of the area. And it's clear from that there are other large run-out landslides in this valley that look a lot like the Oso landslide. So, for example, the Rowan landslide here, which is a monster landslide not very far from the Oso landslide at all, that clearly ran out a long distance and in fact looks to have pinned the North Fork Stillaguamish River here along its edges. The LiDAR wasn't the first thing to show this. The geologic mapping in this area has long showed landslide deposits up and down this valley. So we know that landslides exist here, but the key question is, well, how old are they? And you can imagine that it's possible that many of these long run-out landslides would have happened after the glaciers retreated some, 14,000 years ago, that would have destabilized the hill slopes because, you're going to carve dramatically down into this weak material, and that could set up a lot of failures during that transition. So the question is, are these all really old failures that are no longer very active, or are they happening consistently throughout the Holocene? And so that was the question that we set out to answer. And to do that, we we went and first created our own map of landslides in this area from the LiDAR. And in this case, this is Sean's map of 24 landslides along a 6-kilometer stretch of river valley. But since then, there's been an update to that, and Adam Booth has a really awesome map here where we've mapped out over 200 deep-seated landslides along the 25-kilometer stretch of the river valley. And I hope some of you had the chance to see Adam's excellent presentation on this in a talk yesterday and a poster today. It's exciting to expand this work. So one way to try and get some information about the timing of these failures is to look at surface roughness. This is a long-standing technique that geomorphologists have used, and it's a pretty simple concept, right? After an event happens, you're going to really significantly roughen the hill slopes, you're going to have hummocky topography, and then through time, as the landscapes adjust and the hill slopes diffuse, you will see a much more muted signature and a much smoother surface. And so this is a simple map made with just the standard deviation of slope as a roughness indicator here, with the roughest slopes, or the highest standard deviation represented in blue and the lowest in green. And as we would expect, the OSO 2014 landslide comes out as the roughest thing, and the Whitman bench and these flat surfaces come out as the lowest roughness indicator. And so that's exciting, but it's not enough, right? Because if we want to really know something about the timing, we need to know something absolute and not just relative. And so for that, the kind of gold standard, of course, is finding organic material. So Sean is pointing, it's hard to see in this picture, he's pointing at a buried log in a landslide deposit that he was able to find in the Rowan landslide. And so when possible, what we want to do is we want to radiocarbon date material from trees or other wood that was buried and killed in the slide, and then we can put limits on the timing of the landslide in that way. And so Sean did his due diligence. He scoured all of these landslides and was able to find actually a pretty large amount of material to date. So we were able to put some absolute ages on the Rowan landslide as well as the Headache Creek landslide right next to Oso. And then we also got some information on a landslide across the way and on a fluvial terrace, which is important because it gives us some information about the timing of when the Stillaguamish carved down itself. So we wish that we could find wood in every single one of these landslides, and in fact, I wish we could do that for the whole state of Washington, but of course that's not possible. In many ways, it's like finding a needle in a haystack, and so we can't always find the wood, and it's really cost prohibitive to date every single landslide. And so we decided that we would try and marry the carbon ages that we had with the surface roughness information that we had in order to calibrate a roughness age curve. And so what I'm showing here is a plot of the carbon age, the absolute age on the y-axis, and the surface roughness metric on the x-axis. And then I have the OSO 2014 landslide is anchoring our curve here, and then we have the other landslides that we were able to date. Finally, the river terrace provides a high bound of what the oldest possible landslide would be in the valley. And then we fit a curve to this, and from this we can actually estimate or predict what the ages would be for the other landslides in the valley, where we can easily get roughness information from the LiDAR, but don't have actual age information from wood. And if you're wondering, well, is there any physical basis for this form, or are you just basically curve fitting here? We explored that by setting up a model. This is a model from Adam's work here, which is pretty neat. So if you start with the OSO 2014 landslide with the LiDAR from flown after that event, and then you just use a simple nonlinear sediment flux rule here to basically diffuse the hill slopes, you can run that model forward through time, and this is what the Oso landslide is going to look like in 12,000 years, and it looks a lot like actually some of the older landslides in that valley. And what you can do also is you can plot what the curve would look like from each of those, and what he did also was used a range of hill slope diffusivities to test out a bunch of those. And what you can see is that in each of these cases, you have this exponential decrease form as we would predict from the actual data that we have. And so we think there's a real basis for this kind of curve. And so this is really exciting because, well, one, what we've learned in this valley is that there's actually a long history of deep-seated slides here. So Sean, this is a figure from Sean's paper where we've color-coded these landslides by a bin. So the oldest are over 5,000 years old. Those are shown in blue. The youngest in red, and in yellow and green you can see here. What you can see is that there's a long history of deep-seated slides in this valley. And we're quite excited to expand this, as we've already done, up and down this valley, and also to other locations. So, for example, for the rest of Sean's PhD thesis, he's hunting for Cascadia earthquakes from previous M9 ruptures, and we're hoping to use this method to help us with dating other landslides in the area when we're on the hunt for those. So we're pretty encouraged by this new approach, and we hope to utilize it in other places. Okay, so you've been very patient as you've allowed me to take you on a very whirlwind tour, I realize, from the scale of a mountain belt all the way down to the scale of a hill slope. So I'll just summarize that I've shown you some detrital thermochronometry and how that permits an estimate of timing and rate of erosion increase across the southeast Tibetan Plateau. Gives us some hint of when that may have risen to its impressive height. I've shown you some new numerical models in GIS and field observations that allow us to refine a conceptual model of landscape evolution and strike slip fault settings, and some new geomorphic metrics that we can use in assessing fault slip history. And finally, LiDAR and GIS is allowing us to push new boundaries in dating large landslide inventories, which are useful in hazard and risk studies and hill slope evolution. And with that, I will thank you and take questions and put up all the other names that I wasn't able to mention in this talk. So thank you. So does anyone have any questions or comments? Yes.
Do you see much evidence for repeated failure on the landslide in the Stillaguamish Valley?
Yeah, so that's a really good question. He just asked about repeated failures. So, I mean, I think even just looking at the Oso failure, we know that that particular failure happened before, not in the exact same way, but that the same site on the hill slope was remobilizing. So, I think it's a given that some of these landslides are going to be reactivated and going to have happened more than once. And so we assume that with the roughness that we're measuring, that's really recording sort of the last event. Though I will say that we're encouraged by the places that we were able to get carbon data. We see lots of measurements from a single event that are in good, they're all in a similar age range. So we don't think that we're finding wood from one event but taking the surface roughness from another, but that is something that we have to consider as a possibility. Other questions? Yes.
Whether the microphone works.
Yeah.
So the thermochronological data is very sensitive to the thermal structure of the lithosphere. And you would imagine that the progressive growth of the Tibetan Plateau will affect that thermal lithosphere. So how do you think that can affect your results?
Yeah, so that's a good point. So he was just talking about the growth of Tibet might actually, sort of change the thermal structure. And so it is possible that could affect these results. I will say, though, that we worked over a pretty long wavelength. So the topography there is a long wavelength topography. So we're in this case, we did not do anything to consider maybe warping of the isotherms or something like that. Though I will say that you can do that in this model. We just didn't do it in this case. But so it's possible that could have had some effect. But at the rates that we're working on, over the scale that we're working on, and the fact that you basically have really only the only high relief is really just sort of close to the river gorge itself, but those aren't even really gorges up in the high catchment. So I think it's okay up here, but it's a good point that it could affect it.
Thank you.
Yeah. Other questions? Yes. Yeah, that's a really good question. So she just asked about what about if the fault slip rate changes through time? So that's an experiment that I would really like to do, and we haven't done it yet. So the hill slopes, or the strike slip faults that I've simulated so far have been basically sort of like a creeping fault, really. So we haven't really considered either earthquake behavior or changes in slip rate through time, but that's absolutely something that we could do. And I think it will matter how fast the slip rate is changing. So it'll be another competition of timescales, but it'll be really fun to try that out, especially because the faults in Marlborough, as you know, are sort of showing evidence that they are changing their slip rate in time.
So in your strike slip models, if that fault has some fault gouge and that really reduces the strength there, you might expect that convexity to be less?
Yeah.
Is that a way that you could back out strength of fault?
Oh, so that's a good question. So she just mentioned that there might be some fault gouge, and you know that would change the erodibility along the fault proper. So that's something else that we don't have in these models, but would be very exciting to include. And other people like Sam Roy and Peter Coons and Fedra Upton and others have been thinking about what damage on faults does to the geomorphology of the system. And I think that's a really good point, that if you have a highly erodible location along the fault from damage, that this would certainly change the game. And I think one thing that it could do, it could enable the rivers to incise dramatically along the fault. So you guys may have noticed in those simulations that, as I said, you never get an offset longer than basically the width of the channels, or the spacing of the channels. But in real life, there are places where you have rivers that flow long distances along a fault. And so far, we haven't been able to make that happen in this model. And maybe the way to make that happen is to have damage along the fault. And so we're starting to play with that now. And there are sections along the northern San Andreas Fault, like the Wallala River and the Garcia River, where we have rivers that are going way much longer than the spacing of the channels. And I think that there may be something to either the damage along the fault or even the variability in lithology from one part of the fault to another. So that's a really good point, and I think that needs to be explored further. Any last burning questions before I turn it over to Bill? Okay, well, thank you very much.